Let me show my screen. Okay, I will start with recording what we have done in the last lecture. So in the last lecture, we started to discuss the law of large numbers. So we discussed the law of large numbers in the classical setting for identically distributed independent random variables. Then we started to discuss the law of large numbers for Markov chains. And look what we have done. So we had the Markov chain. xi0, xi1, xi2, etc. And we have a function f which acts from the state space of the Markov chain to the real numbers, and we are interested in sums of this form Sn. For example, the important example is the case when the f is the indicator function of one state. Then Sn, this is the number of number of times you visit the state x hat with within the time n, and then Sn over n, this is the frequency of visiting this state. Well, then I introduced some notation. I denoted by, if you have a distribution, possibly a distribution of a random variable, right? Distribution, then it acts on functions by the following formula. And actually, if P, this is a distribution of a random variable, then this formula gives just the expectation of the function f computed on the value of your random variable eta, right? Then I recalled what is the mixing Markov chains. Sorry, not mixing, we call them ergodic, right? Exponentially ergodic. So it means that for any, so that you have unique stationary measure, and for any initial conditions, your distribution at the moment of time n converges exponentially to, in L1 norm, to the stationary measure. We have proven such simple lemma, which states that if your Markov chain is exponentially ergodic, then the expectation of the function f computed at the value of the random variable xi n, which actually equals to the action of the distribution of the random variable xi n to the function f, as we have just discussed, right? It converges to the action of the stationary measure to the function f, okay, which actually can be represented as the expectation of some random variable which has a stationary distribution. The distribution pi the expectation of the function f computed at this stationary random variable. Well, and then we have formulated the main theorem, which is the law of large numbers, which says the following. It says more or less the same that the law of large numbers for identically distributed independent random variables. So let us consider this sum. Let us assume that function f is bounded, and then the sum Sn minus its expectation normalized over n converges in probability to 0. This is the first item. The second assertion is that this expectation over n converges when n goes to infinity. This is just a sequence of numbers, right? So this is just a usual convergence. When n goes to infinity, it converges to the action of the stationary measure pi to the function f. And the last assertion, which immediately follows from A and B, is that Sn conversion probability to the action of the stationary measure pi to the function f. Well, So here I explained some example for the case when f is the indicator function. It means that the frequency of visiting the state x, it converges to just to the stationary probability of the state x hat, which is one of the standard applications of this law of large numbers. And now I am going to prove the law of large numbers, and I think that I will spend the most part of the lecture for this proof because it's quite long. So do you have any questions for about the statement or about the content of the previous lecture? Okay, if no, then let me start the proof of the theorem. Well, proof. Well, I'm going to do exactly the same thing that I have done when I was proving the classical law of large numbers. So I need to establish the convergence of this guy to 0, right? So I will just try to apply the Chebyshev inequality. So let us try to do that and look what it gives. So what I should write? I should write the following thing. I should write the probability that absolute value of Sn minus its expectation normalized over n more than or equal to epsilon, right? So I rewrite it exactly as I have done this while proving standard law of large numbers. I rewrite it up like this, epsilon n. And then I apply the Chebyshev inequality. Chebyshev inequality, which affirms that this is less than or equal to what? To the variance of Sn over epsilon n squared. So epsilon squared n squared. And then look, for the classical law of large numbers, this was almost the end. This was almost the end because we knew that the variance of Sn, it equals to the sum from n equal 1 to from k equal 0 to n minus 1 of variances of f computed at psi k, right? This was the classical setting. This would be true if psi k were independent, but they are not. So basically, this is not true, since psi k are not. They do not have to be independent. And what then should we do? Do you have any suggestions? What could we do? What could we do in our setting when they are not independent? Can you suggest something?
I think that we can still expand the variance and somehow estimate the covariance of f xk xj.
Right, Camille. Right, Camille. That's exactly what I'm going to do. My proof, this is just brute force proof. So I'll just I don't have this formula, but nevertheless I'll write down explicitly what the variance is. By definition, variance, this is that. This is the expectation of Sn minus its expectation squared, right? Then let me introduce the notation which I will use throughout the proof. Mj. This is just for for shorten my notation, I will denote by mj the expectation of f of psi j. Okay, this is a notation. Well, then what is this guy? By definition, this is the expectation of sum from k equal 1 to n minus 1 of f of psi k minus mk, and this guy squared, right? And now I will just compute this square. What is this? This consists of two parts. So the first part, which I like, which is simple. This is sum from k equal to 0 to n minus 1 of what? Of the expectation of f psi k minus mk, all this squared, right? But I have also the second part, which is more complicated. Let me write it down. Maybe I'll do like this. Hop. Yeah. This is two. This was the diagonal part of this sum, and now the off diagonal part. The sum over k and l between 0 and n minus 1. Moreover, k is less than l. So two sums. The expectation of the product f of psi k minus, well, minus mk, and then f of psi l minus ml. Very good. So what is this? Just by definition, this is the sum of variances of f of psi k, right? Plus two sums of the covariances. So this is a standard thing that when you have covariance of some sums, then you obtain a thing like I am now writing down, but I computed it in details. Covariance f of psi k, f of psi l. Perfect. Look, and I will call this, maybe I will call this I1 plus 2I2, okay? And I will estimate these terms separately. Actually, what I wish to establish, I wish to establish that this variance of Sn, so this I1 plus 2I2, it is O small of n square. If this is so, then this guy tends to 0, and then this probability tends to 0, and I get what I want to get, right? I get the convergence of this guy to 0 in probability. So I will show separately that I1 and I2 are O small of n. So let me start with the simple term. Let me start with I1. But this is simple. This is the same that we had in the classical setting. Just I need to note that variance of psi k, this is, what is this? This is up, sorry. I'm sorry. Up, that this, it equals again to the expectation of f of psi k minus mk squared, which is bounded by what? Look, okay, mk. First, I'll bound mk. Mk. This is the expectation, absolute value of mk. This is less or equal than the expectation of the absolute value of f of psi k, right? Because when I put the absolute value inside of the expectation, I get, instead of the equality, I get the inequality. And then because expectation, this is just the sum, right? Then this is called by the triangle inequality. Then this is less or equal than just absolute. Okay, I will do this for the second year students. I will do this in all details. This guy is bounded by sup norm or L infinity norm, as you wish, of the function f. Of the function f, which is by definition supremum over all x of f of x. I recall that the function f is bounded, right? So this is less than infinity. So that's why I have this inequality, and then this equals just to sup norm of the function f. So here, look, here I have this is less or equal than the expectation of two sup norms of the function f squared, which is 4 sup norms of the function f squared. Very good. Then the term I1 is bounded by, look, I have sum of n variances like that. Each is bounded by this guy. Then I1 is bounded by 4n sup norm of the function f squared. Perfect. That's what we need, because this is O large of n. So for sure this is O small of n squared. So this guy will be killed by this n squared under the limit n goes to infinity. So now it remains to study the term I2, which is actually more complicated. Let me formulate the main lemma. So this is lemma. I will separate this up. Lemma, what is the number of this lemma? Let me check. I had theorem 28, so this is lemma 29, right? Lemma 29. Lemma 29, which is the K lemma of the proof. It states the following. It states that covariance of f psi k and f of psi l, it is bounded by constant times lambda to the power l minus k for any k less than l. Okay, for any k less than l, more than or equal to 0. Look, who is lambda? Lambda, this is the same lambda which comes from exponential ergodicity. Lambda, it comes from exponential ergodicity of the Markov chain xi I. So this is the same lambda. I forgot to write down the main thing, that lambda is in between 0 and 1, right? So look, what does it mean? It means when the k and l, these are times, right? So if the time between between which you are waiting is long. So if L minus K is large, then the covariance of the random variable f of psi k and f of psi l is extremely small. It's exponentially small with respect to the difference of these times. It means actually that for Markov, for exponentially ergodic Markov chain, the variables at the moment of time, at moments of time which are one far from another, are almost independent. Well, we know that uncorrelated random variables and independent random variables, these are different things. We know that there exist dependent random variables which are uncorrelated, so that the covariance of them is 0. But morally, we can think that in the Markov chain, these two guys are almost independent. Okay, formally they are almost uncorrelated. You see, this is a very strong property of the Markov chains. This is very strong thing. It means that the Markov chain, like, it forgets its past. It forgets its past when time goes to infinity. And this is very natural, because we know that if the Markov chain is ergodic, then independently of the initial distribution, it converges to the unique stationary measure. And this exactly means that it forgets its past. So it doesn't depend where do you start. The only meaningful thing is what is the stationary measure, right? Because you converge to the stationary measure. Well, so this is a lemma. This is a lemma. So let me first conclude the proof of the theorem using assertion of this lemma, and then let me prove this lemma. So now let us assume that the lemma is proven, and let us study the term I2. The term I2. The term I2. This is the sum of the covariances. So it is bounded by the lemma 29 by the sum from over k and l between 0 and n minus 1, this constant c, and then lambda to the power l minus k. Okay, l minus k. So let me denote this by I. This L minus K denote this by I, and then I have constant. Then this I, it changes from 0 to n minus 1, right? From 0 to n minus 1, and I need only a rough bound. Look, how many terms for each fixed I do I have? So how many pairs of L and K for each fixed I have? Not more than n, right? So just a rough estimate is n here, lambda to the power I. But then this is bounded by sum from zero to infinity of lambda to the power I. This is geometric series. So this equals to Cn over 1 minus lambda. Nice. You see, so the term I2 is also bounded by some constant times n. So this is O large of n. In particular, it will be killed by this n squared. It will be killed by the n squared. So let me then conclude the proof of the theorem. Now we see that the probability we are interested in, that Sn minus its expectation more than or equal to epsilon, it is bounded by well, I will rewrite the estimate I have already written down, epsilon squared n squared which is bounded by okay, so I have I1 plus 2 I2, right? So I1 is bounded by this guy, then I have 4 n norm of f squared over epsilon squared n squared plus 2 I2, 2 constant c, n, and then here we'll have y minus lambda epsilon squared n squared. Look, and this guy goes to 0 when n goes to infinity, as well as this guy, right? So this is goes to 0 when n goes to infinity. So the theorem is proven. Modulus lemma. So let us again take a look at this lemma. This lemma actually states, this lemma states that, as I've already mentioned, that the process becomes like exponentially uncorrelated with time, but we see from this proof that such exponentially uncorrelated processes, they are as well as processes for which you have just independent random variables. Because you see, for the first process with independent random variables, we know that the variance for those processes, here we have the equality. So we would have just the bound, just this bound. We would have that the variance grows linearly. But for the processes which are exponentially uncorrelated or decorrelated, we also see that the variance actually grows at most linearly. See, so morally, this is, in fact, everybody understands that the two assumptions. The first, so we can consider two different situations. The first situation is when your random variables are independent, right? You have a sequence of independent random variables. The second possible assumption is that you have a sequence of random variables which are not independent, but which are exponentially decorrelated in this sense. In fact, everybody understands that these two assumptions are almost equivalent. So the theorems which you can prove for the first assumption, for the independent random variables, usually you can prove the same theorems for under the second assumption that your random variables are exponentially decorrelated. And this is an example, right? This is an example how it works. So, but now for Markov chains, this is not for granted that the random variables are exponentially decorrelated. It should be proven. So let us establish this lemma. Do you have any questions till the moment? Proof of lemma. No questions. Well, there is a question in the chat. It's very nice. No, professor. So no questions. Well, okay. I wish to start with introducing some notation. I will, as usually, denote by pi stationary distribution. So I recall the notation mk, which is wait a second. I'm sorry. So let me maybe postpone slightly the proof of the lemma because I haven't yet proven the theorem actually. Why? Because in theorem I have not only one assertion, I have 3 assertions, right? But now I have proven I have 3 assertions in the theorem. Now I have proven only the first assertion, only this one. It remains to prove the second and the third. Yeah, so this was assertion A. Now let me prove the assertion B. Assertion B states that the expectation of Sn over n converges to the action of the stationary measure to the function f. Let us prove this. Let us prove this. Well, so this is not the end. Assertion B. So we need to study expectation of Sn over n. Well, but look, what is this? This is 1 over n sum of expectations of f of psi k from k equals 0 to n minus 1. But we had a nice small lemma in the previous lecture, which said the following here, which said that these expectations, they converge, even exponentially converge to the action of the stationary measure to the function f, right? So we know that these guys, they converge actually to, when n goes to infinity, to the action of the stationary measure. It's the function f, and then this is small lemma which I leave for you, which is like lemma from the first semester of the first year of your study, is that if you have a sequence xn which converges to some x when n goes to infinity, all them are real. Then sum over n, 1 over n of these guys xk, they also converge to x. So this is exercise. This is very trivial exercise. Actually, how this convergence is called, do you know? This convergence has a special name. Do you know the name of this convergence? No? This is called Cesaro convergence. And this guy is called Cesaro average. In fact, this is a standard object in dynamical systems. So this is quite popular type of convergence. So in fact, lemma claims that standard convergence implies the Cesaro convergence. Of course, the inverse is not true. In Russian, this is Cesaro. Well, so you see that this lemma, it implies, this lemma together with this convergence, they imply that this guy goes, when n goes to infinity, to the action of the stationary measure pi to the function f. So that's what we wanted to prove. Right? Is it clear? Now we have the item C, but this item C is immediate. I think that I even shouldn't write the proof, because look what the item C states. It states that, okay, item A states that this is true, item B states that this is true, and item C, this is just you take this guy and put it to the right hand side and use the item B, right? So item C is indeed immediate. Here you have some, in fact, you have a delicate moment that you can, I mean, are allowed to take this guy and to put it to the right-hand side. We get used that when we have the conversions, it is like always like that. But in fact, the convergence is in probability, this is some special type of convergence. So it isn't evident that we are right to do this, that we are allowed to do this. But in fact, we are, and this follows from some lemmas which we have proven in the previous lecture on the convergence of in probability, which affirm that the sum of two random variables, if sum of two sequences, if you have two sequences, each of them converge in probability, then their sum converges to the sum of the limits, right? So here you have some delicate moment, but everything is okay. So this is immediate corollary of A plus B. Well, questions? If no questions, then I pass to the proof of my lemma on the exponential decorrelation of the random variables f of psi L and f of psi K. So notations I will use. Yeah, pi. This is of course stationary measure, stationary distribution, or stationary state, as you wish. All this is the same. Mk. This is the expectation of the function f of psi K, and also yeah, the new notation which I would like to introduce is the following. This is covariance with sign infinity, with index infinity of f of psi K, f of psi L. In such a way, I will denote the following, like almost covariance. Look, normally to have a covariance, I should subtract here mk, right? But instead, I will subtract pk. So this is the component number k of the stationary measure. I recall that this guy actually it goes to pk when n. Whoa, sorry, I have some problems. Why pk? Not pk, of course not pk, because k, this is time, this is not component, right? Sorry. So this is the action of the stationary measure pi to the function f. Yeah. So I recall that this guy, we know from this small lemma of the previous lecture that this guy converges to stationary measure pi acting on the function f. And then you see, like I replace in the definition of the covariance the expectation at the given moment of time, but by its limit when time goes to infinity, and call this covariance with index infinity. Okay, and let us also denote. Okay, we will write let delta KL. This will be the difference of the standard covariance with this new covariance with the index infinity. And of course, what I would like to prove, this is that this delta is small. So I will show that this delta KL is small. Yeah. This is my first goal, actually. The second goal, so this is like step one, okay? Step one of the proof. And the objective of the step one, this is to show that delta KL is small. In the step two, I will prove that this covariance is small. And together, these two steps will give that this covariance is small, like exponentially small. So exactly in that sense, in which I need to prove the lemma. So, okay, from this lemma, from this small lemma in the previous lecture, which I have already mentioned several times, for example, which I have already used here. Let me check the number of this lemma, because now I'm using it already for the third time, so I should give the reference. So this is lemma 22, right? This is lemma 22. No, 27. This is 27. 27. So lemma 27 states that mk converges to this limit, to the action of the stationary measure pi to the function f exponentially. That is, it is bounded by some constant times lambda to the power k. Okay. And then now I'm going to show that this guy is small, right? So then to do this, I will use the following trivial identity. If you have A, B, C, D, if these are some random variables, then we have the following simple estimate. Expectation of A, B minus C, D in absolute value is bounded by expectation. What do I want? I want to have A minus I want to have A minus C times B plus the expectation of what remains. Look, I have A minus C times B. It remains C times B minus D, right? Am I right? Look, A minus, I have A times B minus C times B. It is cancelled, so it remains minus C times D. Yes, that's what I need. Right. So this is triangle inequality, and now I will apply this inequality with A equals to this guy, B equals to this guy, or maybe not, or maybe not. Let me think. Let me think who is who. Wait a second. So I wish to have the difference of the expectations. So here I should have A minus C. No, I think that, wait, it's just the same. Well, let this one will be C, this one will be D, and A and B, this will be the corresponding parts of the usual covariance, where it is written the. Okay, let me write it down again, maybe. Maybe I'll write it down just here. Standard covariance. this is the expectation of f of psi k minus mk times f of psi l minus ml, and this will be a and this will be b. I think that this will give the result I want. Let us look what we get. So delta KL is then bounded by what? So expectation of a minus c times b. Look, a minus c. So a minus c. I have what? I have f of psi k is cancelled, so it remains mk minus this action of p to the function f. Actually, the order is not important. I mean, I can write instead this guy is minus and this guy is plus. It is important because I'll put the absolute value. So I should multiply by b. B is then f of psi k minus m. Sorry, f of psi l. This it isn't written properly. This is psi l. Psi l. F of psi l minus ml. Well, plus the second expectation, its absolute value. So here I should write c. C, this is this guy. So f of psi l minus its limit times b minus d. Who is b minus d? B minus d is again ml minus p action of p to the function f. Okay. So now the question for the audience.
Sorry, just one index in the second summand, f c l. I think that it's k.
Yeah, you're right, Camille. Thank you. You're right. This is my arrow. Yeah. Okay. So the question for the audience: what can you say about the first summand? What can you say about the first summand? I claim
it's 0.
Exactly. This is 0 because look, because this is just a constant, right? The first term is just a constant. So I can put it in front of the expectation, and then I should take the expectation of what remains, but the expectation of f of psi l, by definition, this is ml minus ml. So this is just 0. Nice. So it remains to study the second term. The second term is not 0, of course, because what do we have? Because we have here I can also put the this constant in front of the expectation, but then it remains what? It remains here. This is mk minus p action of p to the function f. But it should be small because we know that these guys converge here, right? So also I should put the absolute value. Namely, according to this lemma 27, we see that this is bounded by some constant. Well, this is look. Normally, I should write down here the constant c squared, but since by letter c I denote various constants, so these constants can change from line to line. I'll write down just c here, right? And here from this term I have lambda to the power L, and from this term I have lambda to the power K. So voila, lambda to the power L plus K. But this is very small. You see, this is very small. Perfect. So now we see that delta is bounded by this small constant, and we can pass to the second step. In the second step, we wish to study this covariance with subscript infinity, right? How will we study this guy? We will first introduce some notation to simplify the writing. I will denote by j what? By j of x. Yeah, by j of x. This is a function. The function f of x minus constant, which equals to the action of the measure p to the function f. So then this covariance with subscript infinity of f of psi k f of psi l, this just equals to the expectation of j psi k times j of psi l, right? So I centered the random variables fk and fl, but not really centered, by like asymptotically centered. Okay, and then yeah, then I just write down the story. Actually, here I think that it can be done. I will use a more straightforward way. It can be done slightly shorter and slightly simpler if you use conditional expectations. But I think that just to maybe to reduce the technicality, I will do the straightforward computation. I will, in fact, implicitly use these conditional expectations, but explicitly you will not see them, because I will just write, in fact, their definition. Okay, so let's go. What is this expectation? By definition of the expectation, this is sum. This is sum over all values. Over all values, which letters do I have? Okay, I have already employed the letters A, B, but this was in step 1. So now we are in step 2. We do not use anymore these notations for A and B. So like I reload these notations. Here I have A, B, probability that psi, well, not A, B, J of A, J of B, probability that psi k equals to A, psi L equals to B. Nice. Now, since we are dealing with Markov chains, we should, when you see probabilities of such type, you should always think about conditional probability, about conditioning. So let us take the condition, but to this end, I should remember who is larger, K or L. I made some assumption on that, but I forgot it. Where is the formulation of the lemma? It is here. So I assume that L is larger than K, right? I assume that L is larger than K. Perfect. Then I rewrite this summation as follows: summation over A and B from X, J of A, J of B, and here I condition the large time to the smaller time, and then I should multiply by the probability that psi k equals to A. Well, who is this guy? Is this guy? This is just component number A of the distribution of my process at time k, right? This is a nice object. I know that it converges to the stationary probability to its component with number a. Well, but who is this guy? Who is this guy? This one. Let me rewrite. The conditional probability that I am in state B, conditioning that at time L, conditioning that at time K, I was in the state A. So this is what? Since my Markov chain is homogeneous, this is just the probability that, look, I can make shift in time, right? Nothing depends explicitly on time because of homogeneity of my Markov chain. So here I can write psi L minus K equals to B, conditioning at the event that psi 0 equals to A. But what is this? Who can say what is this? What is this? Who is this guy? This guy is in fact, look, I have Markov chain in L minus K steps. Do you remember, right? So this is a transition probability of my Markov chain in L minus K steps from A to B. But we know that this equals to the transition probability matrix taken to the power L minus K and its component AB. Huh? Is it clear? Is it clear? This is transition proba in time L minus K from A to B. We also have denoted this as pi. How have we denoted this? Well, I forgot the notation actually. So the transition. Okay. So the notation, yes, the notation was like that, right? AB. So this is one way of thinking about this object. Another way, which will be maybe slightly more convenient for me, just because of the structure of theorems I have suggested to you before, just because of that, just because of the way of writing, is the following: that who is this? This is actually probability distribution, its component number B, at the moment of time L minus K. And here I will write such index A. This is the distribution okay, so sorry. I will let me write it. Let me put it in a different manner. Let us consider psi 0, psi 1, psi 2, etc. And here I will put the upper index A. The upper index A. This is a Markov chain with the same transition probabilities, but with different initial condition. So the probability that psi 0A equals to A, this is just 1. In other words, if you take the initial distribution, which I will denote like that, I will also put here the index A, then its component A equals to 1, and its component like B equals to 0 for any B. And then this guy, this is exactly the distribution of this Markov chain taken at the moment, its component number B, and taken at the moment L minus K. Is it clear? I think that actually we have already discussed this Markov process, and we have discussed that. This is exactly that. Actually, it follows from the fact that this object equals to this object, which we have proven in one of the first lectures. Okay. So now, according to the ergodic theorem, these probabilities, these distributions of my new Markov process, which starts in A, it converges exponentially to the same stationary measure. Because why? That because ergodic theorem states that independently of the initial condition, you have exponential convergence to the stationary measure, right? So here I consider the same Markov chain as we studied before, but just I changed the initial conditions. So this guy is bounded by some constant c times lambda, the same lambda as before, to the power n, right? For any n. Then we see that this guy converges in particular to the component number b of the stationary measure. You see? Very good. And then let us rewrite, motivated by this fact, let us rewrite the sum we are interested in the following manner. So let me subtract from this guy, which I will now write down like this. Subtract its limit. So this is component number b of the stationary distribution. And let me add it again. Then I will get summation over all a and b over all states, j of a, j of b, and then what should I write? Sorry, I forgot how it was. It was like that, so I should subtract and add, right? Then here I have this pb time L minus K here, that fact I start from L minus PB times what we had else. We had else here PAK, right? Times PAK and plus sum over AB, J of A, J of B, PB, PAK. Nice. Look, let us first take a look at the second sum. So you see, I have written this guy as this guy. This is just different notation, in fact. And then I subtracted from this guy PB, and I added this. So now let us first look at the second term. What is written down here? Who can say what is this actually? What is this? Clearly, I can write it as a sum over A of J of A P A K times the sum of J of B of B J of B P B. So what is this? We have already met the object like this. We have special notation for them.
Yeah, that is expectation of GCK, the left hand side.
Yeah. I would better write the action. This is the same. Yeah, Kamil, you're right. But I would better write the action of the measure pk to the function j. Why? Because the second term I wish to write in the same manner. The action of the stationary measure to j. But what is the action of the stationary measure to j? Look, this is the action of the stationary measure to f minus. Sorry, this is my Google. To op minus constant. This is I have rewritten the definition of j. The definition of j by linearity of the action. I have p times f, and look, then I have the action of p to the constant. But the action of p to the constant, look how the action of measure to the function works. It takes the sum of values of function times the sum of components of the measure, right? And if you act by your measure to the function which is constant, say to 1, this is just sum of components of pi, right? And this is 1. This is 1 because this is distribution. If here you have not 1 but a different constant, then this guy is linear in J, so that's why you will get this constant. That's why when you act by pi to this constant, you get this constant. So this is 0. Huh? So this guy equals to 0 because this one equals to 0. So it remains to study the first term. It remains to study the first term in my sum. Well, but it is also A and B are also separated here. They're also separated, so I can write, what do I have? Look, here I have, no, they are not separated because here I have A and here I also have A. But well, this is not a problem because actually I do not need the equality. I need only the upper bound in the absolute value. When I'm writing inequality and above the sign absolute value, it means that I take the absolute value of the left-hand side and it is bounded by what I will write now. So notation. This is notation. If I write that x in absolute value y, it means that absolute value of x is bounded by y. Okay, this is the notation. So here, then I have the following bound. Look, the value of the function j is bounded by its subnorm. So here I have subnorm squared of the function j. And then here I have the summation over b of this guy. The summation over b of this bracket, this gives you the summation over a. I rewrite it. and the summation over B, it gives the L1 norm, of the difference. Of the distribution at the moment of time L minus K with upper index A, times this PAK. This is bounded by according to the ergodic theorem, which states this. So according to the ergodic, to this formula, we get that this is bounded by L infinity norm of J times constant times lambda to the power L minus K times PAK, and PAK, and I forgot the summation over all states A. Look, well, this is just squared L infinity norm, sup norm, which is the same constant lambda to the power L minus K, because the sum of these guys, this is 1, because this is a distribution. So the sum is 1, right? So it remains to estimate the L infinity norm of J, but actually we have already done this, I think. What is this? This is less or equal than the L infinity norm of the function f plus the L infinity norm of the constant, which is of course just the absolute value of this constant. This is bounded by 2 sup norms of f. Right? Sorry, I sometimes I say L infinity norm, sometimes I say sup norm, but this is the same in this context, right? Well, so this is bounded by 4 sup norms of f squared times constant times lambda to the power L minus K. Nice, because now it remains to just to collect the results of the 2 steps. The first step said that the difference of the covariance of the normal covariance with this modified covariance is bounded by what? But by constant times lambda to the power L plus K. The second step affirms that this covariance, this modified covariance, it is in turn bounded by this guy. So in the result, we have that the covariance, the standard covariance we are interested in, is bounded by in absolute value constant C. Okay, some constant which may depend on the function f, because here you see this f is included, times lambda to the power L plus K plus lambda to the power L minus K, 2 constants f, lambda to the power L minus K. Okay, so that's exactly what we wanted to prove. You see? So the proof was quite technical, but it is natural. It's more or less straightforward. There are not a lot of tricks. The only thing is that you should do, you should just all the time try to use the ergodic theorem, right? To approximate the objects by their limiting objects using the ergodic theorem. Okay, what is natural that in fact, if you look at the constants, we get in the bounds always f sup norm squared of the function f. So here it is visible. Above, I think that it is hidden. Look, yeah. So here actually it is hidden, but in fact, if you analyze the proof, you will see that this constant c, it also behaves f as the norm of the function f squared. This this comes from, in fact, it was hidden in this lemma 27 because this constant c, it depends on it behaves as supernorm of the function f, and here you have like square of this constant. And when we estimated the first term of the decomposition of the variance, it also was bounded by the square of the sup norm, and this is very natural that everything behaves as the square of the sup norm just because the object you consider, just because you use the Chebyshev inequality, you wish to estimate the variance, and the variance, it behaves quadratically, right? But this is the variance of what? Of the sum of such sum, right? So it should behave quadratically in the norm of this function f. Well, do you have any questions on the proof? No questions, right? No questions. And our time is almost over. Okay, so well, then I think that we will stop for today. So for the next time, I hope that the control work will be checked till the next time. Then we will discuss some problems from the control work. As well, I plan to discuss some applications of this story on the Markov chains. Actually, I hope to start it today, but I didn't manage. So I will start with some simple applications, which will be easy to listen and easy to understand, and then I will spend maybe one lecture to explain some more complicated applications which are related to decoding texts. So I'll just explain in details how one can decode text. If you have a text which is encoded, how you can decode this text, расшифровать текст, how you can decode this text using the Markov chain. Well, let us finish.
Sorry, can we discuss one problem from the last set?
Yes.
So this is a third problem about law of large numbers for about classical.
What was the question? So if the classical law, if the classical law of large numbers follows from the law of large numbers for Markov chains, right?
Yes, for random variables that have like every state with equal probability, we can just take a full graph for a Markov chain, and with every edge weighted the same. But for other cases, I cannot think of an example of a Markov chain.
But for which other cases?
For case when our variables, random variables xi are not distributed like
are not identically distributed, right?
No. They are identically distributed by xi distributed. For example, it takes value 1 with probability 1 over 3 and 2 with probability 2 over 3.
This is just the same, more or less the same. Look, because what do we have?
Oh, yes, right. We can split. We can split actually states. Oh no, sorry.
Because you have independent identically distributed random variables, right? Then what does it mean? It means that you have certain, so the probability at the moment of time k, the distribution. This is just the distribution by this d. I denote distribution. Sorry. I have special letter for distribution. This is, I denote this pi psi 0. So this is just pi psi 0 for any k. Yes, I write psi 0 because all they are identically distributed. So this is constant with respect to k, right? So this just means,
but not every state is equal probability.
Yes. So this constant with respect to k. I mean that this of course vector which is non-trivial. This is some, you know, nu1, nu2, nu3, etc. So the sum of this nu j, this is 1. Of course, this I don't recur that they are equal. Yeah, I don't recur it. But this is constant with respect to k, so it doesn't change with respect to k. But it just means that the transition probability matrix pi, it should be equal to identity, right? Identity. Because what do you have? You have that pi n equals to pi to the power of, not like that, pi.
But in this case, these random variables are not independent.
Why? They are?
Because at the moment of time k, we cannot attend any state other than state on the diagonal.
You're right. So what I've written down,
we need a full graph, and
you're right.
It seems that we can replicate some states with like take a fractions of probability and
yes,
assign
you're right. You're right.
of this.
I've written something very stupid because I've written the graph which is like that. So you have first state, second state, third state, and every random variable goes to itself. So it means that if you had so I've written a graph for the chain like that, psi 0, psi 0, psi 0, psi 0, right? So of course these random variables are not independent. So indeed we should do as you suggest. So we should take our graph and then look, then assume that at the initial moment of time I am, say, in the state 1. If I am in the state 1, then I should what should happen? Then at the moment of time, at the first moment of time, I can be in any state independently of this one, but with probabilities, with this probability distribution, right? So it means that okay, if I have this vector on the example, let me it will be nu1, nu2, nu3. So this is the distribution of the random variable psi 0, which is the same as the distribution of random variable psi n for any n, since they are identically distributed, right? So from 1 I should go to 1 with probability nu1, to 2 with probability nu2, and to 3 with probability nu3, right? And from 2 I should go to 1 with probability nu1, to 2 with probability nu2, and to 3 with probability nu3, right? And from 3 to 1 I should go with probability nu1. From 3 to 2 I should go with probability nu2, and to itself with probability nu3, right? Then look, then what is going on? Then indeed at each moment of time, the probability to be at given, so I have the same distribution. So this is satisfied. This is satisfied that this is constant. because look, independently on where I start, I will be at the position 2, for example, with probability nu2. Because if I start at the position 1, then I arrive at the position 2 with probability nu2, and this is the same for all other states. It means that the probability that at the second step I will be at the state 2 equals to nu2, right? So and the same with the other probabilities. Okay, so is it?
But
okay?
It is okay, but we also need independence from future because the family of these random variables is independent.
We need the independence from Camille, wait. What is the assertion? My assertion is once I have such sequence of random variables, assume that I have sequence like that, then I claim that xi0, xi1, xi2, etc. is a Markov chain with graph.
Oh, okay, yes.
With graph,
yes.
Yeah, given by star. Yeah. If you wish to construct such Markov chain, just take identically distributed independent random variables, right? So we know that they exist. Okay.
Okay, and this Markov chain is clearly mixing, and
yeah, this is clearly
therefore
mixing. This is clearly mixing.
ergodic
You see,
exponential.
this is slightly strange because I mean, if you change the so if you change the initial distribution for this Markov chain, you will not get, of course, anymore the sequence of identically independent random variables, right? They will not anymore identically distributed, and I think that will not anymore independent, but their distribution will converge to the distribution of these guys. So somehow, if you have graph for Markov chain of this type, it means that its stationary distribution can be modeled by a sequence of independent random variables. You see? So for any Markov chain, you may find a random variable with stationary distribution, since if you know for any distribution there exists a random variable which has this distribution, right? Which has this distribution. But what I want to say? Wait, what I want to say? Yeah, but the point is that if your graph is like that, if your graph is like that, then you can find a sequence of random variables with stationary distributions such they are independent and they are involved into this Markov chain. Okay, so do you have any more questions?
Okay.
So then let us finish for today.
До свидания.
Счастливо.